Let's start by understanding the simple equilibrium across a semi-permeable membrane. These are two compartments, compartment A and compartment B, separated by a semi-permeable membrane which allows all the ions to pass through. Now let's add on the side A 10 ions of potassium and 10 ions of bicarbonate. On the other side 10 molecules of potassium and 10 different ions like chloride we will have. So here it is 10 potassium plus 10 potassium here and 10 bicarbonate initially and 10 chloride on this compartment. Now when we added initially, both the sides are electrically neutral, that is the number of positive ions on both the sides is equal to the number of negative ions. For example, here we have 10 positive and 10 negative, so net charge is 0 here, and similarly 10 positive and 10 negative, the net charge is 0 here. So there is no electrical gradient at this point when we have applied, but what is present here is that there is a concentration gradient of bicarbonate and chloride ion. That is, bicarbonate is have a high concentration here, so it is going to move towards this direction, whereas the chloride from this direction is going to move in this direction. So after equilibrium, this bicarbonate will also equally distribute on both sides, and for the same the chloride will also equally distribute. So after equilibrium, 5 bicarbonate here, 5 bicarbonate here, and 5 chloride over here and 5 chloride over here. So now the membrane, both sides of the membrane, there is no concentration gradient. All the concentration of all the ions are also equal, like for potassium, bicarbonate and chloride, and there is no electrical gradient also, that is net charges on each side is 0. So this is what happens in a simple equilibrium, that is when a membrane is permeable to all the ions will equally distribute and there will not be any electrical gradient also. But this entire equilibrium is going to change if we add one of the non-permeable ions on the one side. Let's take the other two compartments which are again equal, A, B, but this time we are going to add 10 ions of potassium and 10 ions of proteins, which we will call it as P minus. On this side we will add 10 ions of potassium and 10 permeable ions like chloride. So this membrane is permeable to all the ion except this protein. So this is at the beginning, that is we are adding 10 potassium here, 10 potassium here. We have 10 protein molecules which are anions, and this is impermeable, that is going to stay only on side A, it is not going to move the other side. But initially we are adding 10 ions of chloride here to the side B. Now in the beginning we don't have any electrical gradient, that is the net ions in this side is 0 and net ions on this side, this net charges on this side is 0. But we have a chloride gradient of chemical gradient, that is from high concentration to low concentration, the chloride is going to move from here to here. The potassium is equal on both sides, so it is at equilibrium, but the chloride tends to move towards this side. Though the protein molecules have a concentration gradient, but it is not going to move to the other side from high to low because it's impermeable. So what will happen if this is allowed to undergo equilibrium? This chloride molecule moves from the 10, it attains a equilibrium. Let's assume like here it becomes 5 and here it becomes 5 molecule. Now at this point of time we don't have equal distribution of charges on both sides, isn't it? The amount of number of ions on this side is positive is 10 but negative is 15. So we have 5 negative charges which is extra on this side. We have 5 positive charges extra on this side. Though there is no chemical gradient for potassium and for chloride, they are both are in chemical equilibrium, concentration gradient is not there, but there is an electrical gradient of more negativity on this side and positivity here. So now what this negativity is going to do, this negative charges is going to attract the positive charges from here. Though the reverse also will happen, that is the positive charges will attract negative charges from here. But let us consider the first situation and try to see what happens. The increased number, the only positive ion which can move from this side is our potassium. So at equilibrium, this potassium is going to, this 10 is going to again redistribute. 10 on both sides is now going to become, let's say, 15 on this side and 5 on this side. If this point we have a the charges, the electrical equilibrium, that is both the side the number of charges are now 0, that is 15 positive and 15 negative, so net charge is 0. Here 5 positive and 5 negative, and the net charges is 0. And protein is not going to move over there, it's impermeable. Chloride is in equilibrium, but the potassium is now here, it is in high concentration. So there is a chemical gradient for potassium here. The potassium is going to have a gradient to move towards its low concentration from here to this side. So if potassium ion moves from this side, that is a positive ion goes towards this side, it will add up one more positive charge here, and there will be net negative charge on this side of the molecule. But the concentration gradient is driving the potassium still towards this direction. So gradually more and more positive will accumulate on this side and negative will accumulate on this side. Now once the sufficient negative charges appears on this side, after say few molecules have moved, let's say let's move 3 molecules and see what happens. Here it is 12 molecules of potassium, and here it is 8 ions of potassium. So here it is like that. Now there is a concentration gradient still driving the potassium here, but since there is a net amount of positive charges over here, that is 3 positive extra is present over here and 3 minus is extra present over here. So this negative charge is now going to oppose the potassium ion going to move this side. So this will, the chemical gradient is working on this side, the electrical gradient is working on this opposite side, that is it will tries to push the positive ion from this side to here because there are too much positive charge over here. So this point of time, when the electrical gradient on one side becomes equal, that is electrical gradient towards one side, that is pushing from B to A, will become equal to the chemical gradient which is pushing the potassium from A to B. If both this electrical and chemical gradient is going to become equal, then there is not going to be any movement of potassium ions. Though there will be movement, but there is no net movement. So one ion will move from here and one ion will be pulled back by this gradient. So both the gradients are work equal and opposite strength. So that there is an equilibrium, but there is an electrical gradient and there is a chemical gradient, but they are equal and opposite to one another. This is called as a Gibbs Donnan equilibrium or Gibbs Donnan effect. That is, a presence of impermeable molecule will initiate unequal distribution of ions on both sides and unequal distribution of charges. And such effect also causes the development of membrane potential across the membrane. So that is how the basic membrane potential develops, that is because of an impermeable ion on one side generating concentration difference, electrical difference, and then ultimately development of membrane potential. Let's see what actually happens on a cell. In a cell we have an impermeable, this is intracellular compartment and this is an extracellular compartment. In the intracellular, the proteins are the impermeable ions and potassium is the matching number of positive ions. Whereas in the extracellular compartment, sodium ion is the positive ion, but it is again impermeable. At resting state, the membrane is not permeable to sodium, and we have chloride ion, which is matching the the concentration will be matching the number of sodium ions in this compartment. So there are two impermeable ion on both sides. This is going to retain all the potassium in this side compartment itself, and sodium is going to retain all the chloride in this compartment. So potassium and phosphate are high concentrated in the intracellular compartment, and sodium and chloride are concentrated in extracellular compartment. Now these two are not permeable. The potassium concentration gradient is going to drive it on this side, and chloride concentration gradient is going to drive on this side. When this concentration gradient pushes them, the potassium ion coming here without any negative ion going to accumulate here more positivity and induce a negativity over here. The same effect of chloride ion moving towards inside is going to create a positivity on this side and induce a negativity on here, because chloride is a negative ion. So this sometimes is referred to as double Donnan effect. That is, one side, both the sides of the membrane, that is, so impermeable ions are present and they are contributing to the generation of membrane potential, called double Donnan effect. In the previous slide, you might have seen that when only one side there is a Donnan effect, there is going to be unequal distribution of number of ions. That is, at the resting state, here there is 12 plus 5 plus 10. We have 37 ions, whereas here only 13 ions on this side. If such thing happens, the water is going to shift from one compartment to other compartment and going to create a swelling of this side, and again the concentration difference is going to change. So it's not a stable state. But in a cell, we have a double Donnan effect. That is, both the sides there are ions moving. This is potassium is moved in this direction and the chloride is moving in this directions, which is going to avoid any unusual accumulation of ions on one direction. Again, sodium potassium ATPase is also helping in pumping the ions, which are excess ions which are moving, and going to stabilize the osmotic gradient between the two compartments. Thank you.